Section 3.3 introduces us to a process called completing the square. It's a way for us to solve quadratic equations, and it's going to be broken up into two parts. In order to do so, we're going to have to build a perfect square trinomial. In this situation, you can see that if we put a 9 on both sides of the equation, we would have on the left side a perfect square trinomial. That's going to factor into such a way that we're going to have one x that we can solve for. In example 1, we're asked to solve this quadratic equation using square roots. And the trick here is to recognize that the left-hand side is a trinomial, x squared minus 14x plus 49. That's what we know to be a perfect square trinomial. And perfect square trinomials factor in such a way that we get two binomials that are the same, in this case x minus 7 and x minus 7. So you can see how that starts to work over on the right. Notice also that both sides of the equation can be written as perfect squares. X minus 7 is written twice. That can be written as x minus 7 squared. And you know 25 is 5 squared. So when our directions ask us to solve the quadratic using square roots, we're now in that position. The inverse operation of squaring is to take the square root. When we take the square root on the left-hand side, the purpose is for us to get closer to being able to say x equals. There's a minus 7, there's the square. When we take the square root, that's going to lift off. When we do that, however, be sure to include the plus or minus on the right-hand side. It's the square root of 5 squared. You know that's going to be 5. Now our goal is to be able to say x equals, so we're going to add 7 to both sides. And so a quadratic, where our highest exponent is a 2, gives us a potential for two answers, and we can say that 7 minus 5 is 2, and 7 plus 5 is 12, and so those are our two solutions to this equation. If we were to graph, we would have points of intersection when x equals 2 and when x equals 12. Here's another example asking us to do the same basic step, and that is solve the equation using square roots. And once again, we are set up on the left-hand side, x squared plus 22x plus 121. They have given us a perfect square trinomial. We're going to factor that the same way we basically did with the last problem, and that is we want to figure out, are there two numbers that multiply to give us 121 and add to give us 22? And more specifically, is it the same number? It's x plus 11 times x plus 11, and so we can rewrite the equation over on the right-hand side. That's what we did in the last problem. The difference here is that when we bring this down to being x plus 11 squared equals 12, we took the square root of both sides last time. If you remember, on the right-hand side it was a 25, a perfect square. Now 12 is not a perfect square, but in order for us to work to get x isolated, to be able to say ultimately that x equals, we still have to take the square root of both sides. So you can kind of get a sense of what's going to happen on the left. It's going to be analogous to the last equation. But on the right-hand side, we have plus or minus radical 12. Now 12 is not a perfect square, but we check to see, is there a greatest perfect square in there? What are some factors of 12? And if you recognize that it could be written as the square root of 4 times the square root of 3, then that could be simplified to 2 radical 3. So we have the ability, when we take the square root of both sides, to just simply have x plus 11 on the left, and we have plus or minus 2 radical 3 on the right. Now there's just one more step. We're going to subtract 11 over to the right. And because we have negative 11 an integer, and we have 2 radical 3 an irrational number, they're not like terms, we're not going to be able to simplify that better. So our two possible solutions here are negative 11 plus 2 radical 3 and negative 11 minus 2 radical 3. Since our first two examples asked us to solve the equation by taking square roots, and we were able to do so because we had a perfect square trinomial on one side of the equation, then it's an obvious follow-up question to ask, how do we create a perfect square trinomial? So in this example, we have the trinomial x squared plus 10x plus c, and we're wondering what the value of c is that's going to make this a perfect square trinomial. So I'd like to remind us of our first two examples. We had a b value of negative 14 and a c value of 49. What's the relationship between 14 and 49? And I hope you can see the sevens and recognize how they're related. We also worked with x squared plus 22x plus 121. 11 times 11 is 121, and 11 plus 11 is 22. So if our c value is what we're looking for, how is it related to negative 14? How is it related to 22? And for this problem, what do we do if our b value is 10? The answer is take half of that value. So what is half of 10? So we come up with 5. And step 2, we want to square that. So we should come up with 25. And our answer will be x squared plus 10x plus 25. 25 is the value of c that's going to make this a perfect square trinomial. And if we tried to factor that, it should come into x plus 5 and x plus 5, or x plus 5 squared. Let's try that one more time. We now have x squared plus 2x plus c, and we'd like to know what value of c will make this expression a perfect square trinomial. To do so, we look at our b value, which is 2, and we take half of that. Half of 2 is 1. We take 1 and we square it. 1 squared happens to remain 1. And so our perfect square trinomial is x squared plus 2x plus 1. The value of c in this expression should be a 1. Go to factor that, and we should have x plus 1 times x plus 1, or we can rewrite that as x plus 1 squared. So blending our skills together, we're now asked in example C to solve an equation using square roots. And in order to do so, we're going to have to first create a perfect square trinomial. So rewrite your equation, but leave a little bit of room on the left-hand side, because our first step is going to have to be to determine the value of C. What are we going to plug in so that that left-hand side becomes a perfect square trinomial? When a equals 1, it's 1x squared, we're going to take half of our b value, half of 18, and square it. So half of 18 is 9, 9 squared is 81, and 81 gets added to both sides of the equation. That gives us a perfect square trinomial on the left, and it also gives us 64 on the right. Step 2, if we look at the left-hand side, the perfect square trinomial, we should factor. So we get x plus 9 twice. We can write that as x plus 9 squared. Now, similar to our examples in the past, we're going to do something to both sides of the equation, hoping to get to x. We're going to take the square root. That leaves us simply with x plus 9 on the left and a plus or minus radical 64 on the right. The square root of 64 is 8. So we have x plus 9 equals plus or minus 8. In step 4, we're working to get x by itself, so if we subtract 9 to the other side, we get x equals negative 9 plus or minus 8. And finally, we want to be able to simplify the right-hand side of the equation. There are two equations there, negative 9 plus 8 and negative 9 minus 8. And so our two solutions for this example are negative 17 and negative 1. In this final example, we again want to solve an equation using square roots. And in order to do so, we're going to make use of a perfect square trinomial. So when we rewrite the equation, in order to have the 2 on the right-hand side, we know that we would like to complete the square in order to have a perfect square trinomial. So to do so, the method that we have looked at so far is to take half of the b value, which is half of 6, 3, square it in order to get 9. And we're going to add 9 to both sides. I also want to just consider that if you can recognize that 6 is 3 plus 3, then maybe you can see how it's going to factor. We're going to get us into x plus 3 and x plus 3. So if we reverse the process and multiply these things by that foiling method, you see that the o and the I terms, 3x and 3x, do give us 6x, and also 3 times 3 for our last gives us 9. So the method of take half of b and square it is perfectly valid, but if you're seeing where we're going to go with the x plus 3's, then maybe that also leads you to 9 for your c value. So we add the 9 to both sides of our equation, and that leaves us with a perfect square trinomial on the left and 2 plus 9 is 11 on the right. Because we have the perfect square trinomial, we forced it to be that on the left. We're in position to factor x plus 3 and x plus 3, which gets us down to x plus 3 squared. We want to be able to say x equals, and so far it is x plus 3, and that expression is squared, so we need to undo those two things. We want to take the square root of both sides. Remember, that leaves us with plus or minus the square root of 11. And finally, we want to move the 3 to the other side by subtracting. The exact two answers for this problem is that x equals negative 3 plus the square root of 11 and negative 3 minus the square root of 11. Depending on the situation, it might make more sense for us to approximate. So you can see in the braces there, negative 6.317 or positive 0.317. Those are close approximations. The equal sign and the line above are the exact answers. This is just something of a visual recap of the work we've done in this lesson. We've been solving quadratic equations, and you know that quadratic equations translate into parabolas when we graph them. Specifically, what we've been finding are the x-intercepts. The first example that we came to x equals 2 and 12, and you can see a parabola with the x-intercepts of 2, 0, and 12, 0. We had other ones like irrationals. The second one was negative 11 plus or minus 2 radical 3. If you notice that the negative 11 is the axis of symmetry, then when we add or subtract that same amount, 2 radical 3, we come to our x-intercepts. It's the same thing over on the right. We're not asked to do this right now, but I think it's worthwhile to keep in the back of your mind as we move forward. In the next lesson, we'll deal with some harder examples.